Okay, so we'll resume our discussion on cyber physical energy systems today. And towards the sort of last 10 minutes of the previous lecture, I briefly gave you a motivating example of why we care about cyber physical energy systems. There's many reasons. I particularly focused on this problem of volatile demand and supply mismatch, and how that directly manifests itself in terms of the cost of electricity or the price of electricity. And towards the end of that discussion, we briefly touched upon this one idea that instead of relying on generations or the supply side of electricity, sort of the end-to-end transmission, instead of relying on the generation side, we can actually request large-scale consumers to reduce their electricity, and that's this idea of demand response, right? So when the electricity grid operator, they realize that there's going to be a peak event, they can dispatch this request to these large-scale consumers, and they can request them to temporarily reduce their peak demand, or even on a hot day. So they can either shut down some systems which are non-critical, or just raise the set points on the thermostats across major components. And so by doing this at a massive scale, you can avoid this peak generation problem or this peak problem at the grid, which causes a lot of issues both in terms of the carbon footprint and the price and reliability of the grid itself. And so in turn, because we sacrifice some comfort or utility to reduce our electricity consumption at each of these participants levels, they get a financial reward for doing that. And so this is a very interesting model. It's called demand response. It's used in many other settings as well, very common. And so what we then touched upon was that if you are a facilities manager at a university or one of these large institutions, how do you ensure that you can temporarily reduce your energy consumption, but at the same time, the cost function or the associated opportunity cost of that reduction is not too heavy, right? So I was telling you that mostly in practice, facilities managers and operations, sort of the staff, they resort to rule-based ideas. And why? Because first of all, rules can capture experience in some sense quite well. So if you have been a facilities manager for decades, you know how a building operates, how it responds when you change some set points. And so you want to rely on your own experience, and you try to describe your experience as some set of rules. But also because there could be some best practices or some guidelines that are observed across different sort of buildings. So most office buildings have similar load profiles. So if someone has figured out the Goldilocks combination for how to change the heating and cooling set points to curtail their load while still maintaining comfort, that rule may also work for you. And so it's not always the case that rules don't work. In many cases, they will get you maybe 90% of your desired building performance. The problem with rules is that they are not consistent, right? So one strategy which was working on day one may not work in all circumstances, right? So we had these two sort of cartoon examples, one where you maintain comfort based on some rule, but you are not curtailing enough, whatever you have promised to the grid operator. And that same rule on a different day can actually over curtail based on environment conditions, but your occupants are no longer comfortable. And when we talk about comfortable, we are mostly referring to thermal comfort, right? And so this naturally leads us to the question, like if you are now the facilities manager, right? You are the CPS expert now. You would want to know that if you don't even know when you change some setting or set point of the temperature of the room or the chilled water, and you'll make all those things will become clear today. That's the whole goal of today's lecture. But at a high level, this is intuitive, right? If you don't even know what's going to happen when you make a change to your system, then essentially you are guessing at best. These rules are some sort of an educated guess. But there is no principled way to even search across different possibilities of these changes. And on the very first lecture, I gave you an example of a large-scale university, where at a university level, there could be 300,000 such control knobs that you can tweak, right? So it's even cognitively, it is impossible for a single person to predict what's going to happen when I change something. And the essence of the question of, the answer to this question is the following, that you really want to figure out what's the best thing I can do. in response to this request from the grid operator, so that first of all I can get a reward, and secondly I have some bound on the thermal comfort that is going to be reduced as a result of these actions I want to take. And so really what I wanted to point across is that when you have questions like these in your systems, they may not be energy systems at the end of the day. When you are faced with the questions like, what is the best thing I can do for my system if I want, going back to the very first lecture, reliability or safety or any sort of metric. Here the metric is maybe your demand response, performance, and thermal comfort cost. And so when you have these questions of what do I do, what is the best thing to do, we are naturally asking, we need to predict what's going to happen in the future based on our actions. And we've seen a way to predict things over time using differential equations and state space models. So naturally, if we had a model of a system, we can predict what's going to happen if we change some control knob or some set point. And so then the game becomes, can you find the best combination of these control actions that will guide the electricity consumption or temperature profile in some desirable region of operation. And so the key word in this approach called model predictive sort of control is what kind of models can be used. So today I'm going to give you an overview of what models are used in the energy cyber-physical domain, but this technique of MPC is universally applicable irrespective of what domain we are looking at. Right, so just to refresh your memory, what are we actually controlling in buildings? We are controlling set points of the heating, the cooling, the ventilation, the lighting, blinds, elevators, whether they're on or off, escalators in the mall, one of them is on, one of them is off. So those are all controlled decisions, but there's so many of these different settings which are possible. So we need a model to let us know that if you change something, this is the desired or the resulting effect of your sort of causal input or control input. So very quickly, this is we'll get to MPC sort of a little bit later in the module, but at a very high level, the intuition is the following, that at any point in time, so at this point in time t, if I have a model of the system, let's say my goal is that the state of the system, which is this blue line, I want to get it as close as possible to this dash line. So this is, in control theory, this problem is called reference tracking. The dash line is a reference, and I want my state or output to track the reference. So if I have a model that tells me how the blue curve will change based on my choices of the input u, what MPC does, or what model predictive control does, is at any time we choose some horizon or some look ahead time horizon or number of steps called a prediction horizon, and we try to come up with the optimal sequence of inputs that will guide my output or state, which is this blue curve, as close as possible to my desired objective, which in this case is as close as possible to this dash line. So we don't know what model we have in this picture, but regardless of that, let's say we come up with this sequence of the red line, which is the optimal sequence that you see by the end of your prediction horizon. You are predicting that you will reach the reference trajectory very closely. What MPC does is we compute this optimal input sequence for the same duration as our prediction horizon, but we only apply the first input to the actual system, which is what we can even do in real world, right? So you can compute chess moves maybe 10 steps ahead, thinking about what my opponent will play if I play this, if I play that. But at the end of the day, you have to only make one move and then wait for the opponent or the environment to react back. That's sort of what MPC is doing, right? So if you see this picture, we compute this optimal sequence, but we only input this control input to the actual system. So at t plus 1, we have made our choice. Then at t plus 1, we analyze the actual state of the system again and redo the entire thing. So sometimes you will hear this term, and later in this course you will also hear this a lot. Model predictive control that's why sometimes called receding horizon control, because this prediction horizon is always receding in time away from you, and you can only act once, whereas you are computing n steps in advance. So we'll study this in more detail. I just wanted to give you some intuition of what predictive control is in the context of buildings. So in the remaining lecture, I want to just give you, today's lecture is going to be about how do we become this domain expert? How do we understand how a building operates and how this electricity system operates? so that we can figure out what would be a useful model, right? So this course is about building useful models. So we have to understand what the modeling problems are in this space and then make our choice of what sort of models we ought to learn. So very quickly, I mean, I don't want to get too much into electricity generation, but electricity systems, you can think of them as having a supply side or a generation side and a demand side. So, as consumers of electricity, we of course are within the demand side, but the distinction or the boundary can be visualized in this sort of picture, that you have the actual power plant or the generator, which we have seen some examples of how they are priced differently based on the time of day and how they generate electricity. Then once you generate that electricity, it is pushed to the demand side through a transmission system, which it can be modeled as a system on its own. It's a massive system which pushes physically the electrons to the local substation in some sense, and then that's distributed through the electricity poles that you see everywhere. Wherever you go, you can find that distribution system which actually brings it to your house or the building. Right? So this is a very, very high level view, but you can model this entire system, right? So you can model how a generator generates electricity itself. So based on the fuel type, how it converts, it could be its own sort of you could have a model predictive controller to optimize the efficiency of a power plant, for instance. That's not what we are going to look into. You can model the transmission and the distribution system, sort of what is shown here. So it's essentially a graph where nodes on the graph are either generators or some buildings. Buildings are the consumers of electricity. So in fact, this model itself is used quite a lot. We don't have to understand what is on this slide to a great extent, but this is essentially the model of a transmission or an electric grid system where everything which is numbered is either is like some kind of a generator, right? And it can have its own internal model, and the links are just telling us how electricity is distributed in the system. The thing which you should be familiar on this slide is this line over here, right? The state of the system can be modeled using some linear dynamics in this very familiar state space form. Okay, so what we have learned previously is actually used in the real world quite a lot. We won't be studying these kind of complex systems at all. So this is not the course for this. So on the demand side, why we are generating all this electricity, because we have to satisfy some electric load, right? So there are different kinds of entities which consume electricity. Roughly speaking, you can think of the demand side having the following key sort of consumers. So in the utility groups and discussions in the community, you hear this term called CII very commonly. So CII stands for commercial, industrial, and institutional buildings, right? So CII is the focus or the target category for demand response, for instance, because they consume large amounts of electricity, right? If you aggregate millions of residential homes, they also compare to large buildings, but individually, if you look at the electricity consumption, industries, institutions, and commercial buildings consume a lot of electricity, and they are the ones which are subject to this volatile pricing as well. Most residential customers are subject to flat pricing, which is changing, by the way. In some parts of the country, like in California and Texas, there is time of use pricing for even residential consumption now. So we've already seen this. I won't, again, spend too much time convincing you that why we choose to focus on buildings, mostly because they are responsible for the largest piece of the pie when it comes to global emissions and electricity consumption, and even energy consumption in particular. What you may not have realized is that within a building, so if you look at a single building and you create this pie chart of where is this building consuming electricity over maybe a year or over a single season, what we have time and again found out, especially for the CII consumers, that the heating, ventilation, air conditioning, and lighting systems always consume the most amount of electricity, right? So if you are the cyber physicist who is asked to optimize this demand response, you want the greatest bang for your buck, right? So if you try to go and convince every occupant that unplug your desktop monitor between 1 and 2 p.m., you may have some success, but what is the accumulated effect on the aggregate power consumption of your building? Maybe not so much, because that's not what is drawing the most electricity consumption. What is responsible for the most consumption is the air conditioning system during summer, the heating system during winter, and lighting systems as well. So that's where you will focus on. If I can model and predict what's going to happen with my heating, ventilation, lighting, I have a chance to actually make an impact by taking some optimal decisions. So that's why we will focus on this HVAC, heating, ventilation, air conditioning subsystems, and that's what we'll try to model in this module. Okay, so a quick word on how will we actually model this, right? So now, in some loose sense, I hope you are convinced that we ought to model the response of a building in demand response. This response could be electric or thermal. Thermal because we care about comfort of the occupants. But how do you actually model a building is the key question. And to sort of motivate this problem, there are many ways you could model this building. So without having explicitly described what is the input and output of the model, I'm just going to give you first a high-level intuition for what are the different approaches to model this physical system, which is a building. And let's say, for the sake of argument, we are interested in some temperature prediction model. Can we predict the temperature in every room, or do we need to create one model for the entire building? How do we even begin this process? So there are three different ways called, you can categorize them as white box, gray box, or black box models. And this white, gray, and black is a spectrum only to tell you how much physics you are using, or how much do you actually know what is going on in the building, as opposed to just looking at data, right? So I think you all already understand to some level that machine learning models would be maybe more black box, but physics-based models are going to be white or gray box. And in this course, in this module, we'll focus a lot on the gray box part of modeling. But what does this process look like for a building? Let's say I have to model this new building, or even an existing building. The first thing I would do is I would need all possible information about the actual working or operation of the building, how it was designed, the geometry of every zone, how large the space which is being air conditioned is, what is the duct layout of the equipment, how is it circulating air inside the building itself. This is what is called a building information model, right? I need all possible CAD files or layout files or design files. I even need to know what is the material of construction of the walls of the buildings, what are their thermal properties, so on and so forth. And if I have all this data available, then some domain expert, which is you, has to look at this data and transcribe it into some sort of a parameter or some kind of a description of, a meaningful, structured way to look at all this data. So like I said, we can go floor by floor. In every floor, you can have different rooms or zones. The difference between a room and a zone is that sometimes a single zone can have multiple rooms. A zone is anything which has its own temperature control or its own thermostat, right? Sometimes 2 or 3 small offices can be controlled by a single thermostat. So you can go floor by floor, zone by zone. In every zone, you can look at every surface, ceiling, walls, floor. Every wall, if you don't know this already, is actually made up of many layers of materials. It's not just one material. So you can even go into the layer of materials in a single wall. You want to look at every equipment. You want to create that model from this information. And the way you create the model in white box modeling is you use some high fidelity physics simulator. Right, so in the community of building automation, we have tools such as the ones shown on the slide, Energy Plus and Transys. Energy Plus is a free tool, and it can take all of this information from the building information modeling itself, and you just initially set parameters of the building, and you can import the geometry, and it will create a model. And when you run a simulation, based on how you set up these usually hundreds or thousands of parameters, it will create the electricity and the temperature profiles given some outside condition forecast or things like that. Right, so the thing to notice, this is a very manual and tedious process, as if it's not that obvious already. These simulators, by the way, are nothing but physics equation solvers. Right, so Energy Plus, to give you an example, was literally designed by physicists about 30 years ago, and it's just a ODE PDE solver. So you are essentially setting up these parameters of the equation and then asking the tool to solve those equations. So the problem with this manual effort is sometimes this information is not always available. If the building is old, even for new buildings, you are skipping something or the actual construction didn't follow the design which exists on paper or in the model. So there's a lot of real world problems which occur. And so what happens is you end up guessing a lot of these values for your simulator. But let's say you even do that, at least you are getting a good high fidelity physics model as the output of this painful process, which can take months and cost hundreds and thousands, if not millions of dollars. You are still not done, because it is not enough to just set up the simulator. You have to ensure that the simulated output or the predicted output of these models that you have set up, they match real world operational data. Only then this becomes the useful model. So you have to tune these parameters, you have to play around with them because you are guessing some of them and assuming some nominal properties which may not actually occur in the real world. So this is an extremely, extremely cost and time prohibitive process to set up a white box model for a complex system. And we are right now just looking at a single building. Imagine how complicated it would be if you have to model the entire campus, which has hundreds of buildings. Not only that, because of the scale of the model, it has so many states, it has so many inputs and so many parameters and control values possible, it's not that suitable for MPC because of the scale. This problem, I should say, is getting addressed, by the controls community, but by and large, the Energy Plus style white box models, which can model every single detail, right from the brick in the wall all the way to high-level electricity consumption of a building. It's just too much of a scale thing for a single model predictive controller. The computation becomes almost intractable. So what's the way to alleviate some of these pain points? Gray box modeling is essentially the same thing as white box, but there is just one key difference, or two key differences. Firstly, we don't model everything in its most physical detail. We can make some assumptions. We can make an assumption that the temperature of this entire wall is uniform across the surface of the wall. I don't need to measure multiple points on the wall to get such temperature. I can assume that the air in this room is well mixed. So I can denote the temperature of the entire room by a single point. Whereas in reality, the temperature where I am standing may be different from temperature at the back of this room. Right, so essentially you have some relaxations in your modeling effort itself. It is still manual though. And the second big sort of difference from white box is we don't really want to use a simulator because we are simplifying the dynamics or linearizing or making these assumptions about lumping things together with a single equation rather than 10 different equations. We want to create a mathematical differential equation model of the system rather than this high fidelity simulator model of the system. Right? So those are the key differences. We still have to tune the model to match real world data, but you can think of this model. And now the next statement, pay attention, because I now expect you to understand what I mean by that. You can create a reduced order dynamical model of the system. So all those terms should be clear by now. Okay, so we know what the order is. I'm telling you that you need less information to describe the dynamics. That's what reduced order is compared to white box. Okay, so in this module, here is what we'll spend a lot of energy on. So literally, you will learn how to create this state space model of a single zone of a building, of a real building. And the model will have this form that is familiar by now since you've turned in your assignment 1. And so, this will have a lot of states, which are these different temperatures of different surfaces of the walls, for instance. It will have a lot of inputs, which are what is the temperature outside, what is the temperature of the floor above or the room below us, if there is any, how much sunlight is coming into the room. And I've said this maybe before, if not, then this is how you should think of heating, ventilation, and air conditioning systems. So humans are essentially hot water bottles or soups, and we are just moving about in a building, and the air conditioning system is taking all that heat that we are producing and rejecting it out to the environment. That's what any air conditioning system does. Okay, so these are all the terms of the heats that we are emitting as we move about and do our business. So talking about heating, ventilation, and air conditioning, this next few minutes or the remainder of today's time, I'm going to tell you how this system works. And this is very important. It may seem like, I'm a computer scientist. Why do I care about what an air handling unit or a chiller is? But that's not the point. The point is, as a computer scientist, as a systems engineer, as a cyber physicist, most importantly, if you don't know how the system works, you don't know what parts you are modeling, what you are emitting, how your model interfaces with the real operation. So I've said this many, many times before. In every module, we will at least have one lecture where we'll put on the hat of that domain. So today we will become this building automation engineer and facilities manager. That's the language I want you to learn. I don't anticipate that you will retain all of this, throughout, and that's only because this is a lot of material to cover in a single lecture. But I want to give you the intuition, the essence of how the system works. So when you leave the lecture today, you will know, at least for the next few weeks, if not for the next few years, how a building operates. Many people don't even know this, whereas we spend majority of our time indoors rather than outdoors. Right? So at the very high level, if it helps, this HVAC system is conditioning us at all times. Right? This is a massive engineering feat which goes unnoticed by almost everyone on a daily basis until something goes wrong. So only when it's too hot or too cold is when you notice, there is this entire ecosystem around maintaining my thermal comfort. But you don't really know how that works. Right? So it goes unnoticed almost. It's almost like the Matrix. Right? You are inside of this, but you don't even notice that it's all around you. So I don't know if this meme is still relevant or not, but if you haven't seen this movie, you are essentially making me feel old at this point. But HVAC is like the Matrix. It's everywhere, even in this very room, and you feel it when you go to work. Or I'd want to do my best Morpheus impression, but maybe not. So we want to know how the system operates. How does it work? I will give you the intuitive understanding today. And it's going to be mostly pictures and storytelling and not too many equations, so you can relax a little. What is the goal of the system? The goal is your comfort. That's why the system exists in a building. The goal is not to save electricity, actually. That is a secondary objective that can we still ensure comfort while being efficient at doing so. The primary goal of any HVAC system, and lighting as well, is to ensure your comfort. But most people think of comfort only in terms of temperature. Some have some, sensitivity to humidity levels as well. You can, based on where you grew up, what part of the world you're coming from, you may be very sensitive to humidity or completely oblivious to humidity levels. That varies from person to person. Even temperature choices vary from person to person as well. There's no global comfortable temperature. But HVAC system does even more control that we don't even notice. One key aspect of HVAC control or operation is to maintain some positive pressure in the building. People don't know this, but buildings are kind of like aircrafts. They are cans which are positive pressure. Not to the same level as a spacecraft or an aircraft, of course, because we are already at atmospheric pressure. But we need a positive pressure because we don't want some dirty air with particulates entering the building. So if the building is at a slightly positive pressure, it's trying to push air out. So that outside air cannot just come inside the building on its own. Then there are some ventilation aspects to the HVAC operation, which we don't realize. So many people, they want to actually feel the airflow as well. If the flow is very minimal or you can't feel the ventilation or the flow of air, even if the temperature and humidity are right, you will still feel discomfort. And not only that, it's almost required by some standards and building operation code that you have to recirculate or refresh the air out. Otherwise, this hot water bottle is generating methane and carbon dioxide and whatnot. If we keep recirculating that air, everybody will feel dizzy without realizing what is going on. So that's the goal of HVAC, to ensure many dimensions of comfort. So today I'm going to tell you how do we do that, right? How does this system work? So at the intuitive level, and I apologize why this appears as if this image is from the 1970s, but at a very intuitive level, a heating, ventilation, and air conditioning system, it has 5 loops, right? So this is how I understand the system, so I'm going to teach you the same way my intuition is. And this is how I first grasped this enormous system. When you were a kid, you may have played this game of hot potato, or there's many variants of this. Essentially, someone throws an object or a hot potato at you. You don't want to hold it for too long. You pass it to the other player. The other player passes it to someone else. And then when the music stops, or some criteria happens, the person who has the hot potato gets a punishment or whatever, or a reward. That's what a HVAC system is. We are generating heat, which is this hot potato, and the air system takes this heat and passes it to the water system. The water system takes this heat and passes it to the refrigeration system. The refrigeration system takes this heat and passes it to the cooling tower. The cooling tower takes the heat and ultimately gives it to the environment, which is what the goal of any HVAC system is. So a very simple way to sort of remember its 5 loops is this, it's like an Olympics logo, right? So like 5 colorful loops. So let me give you an intuition again about each of these loops. What happens on the building side all the way to how does that heat get rejected to the outside environment. So at the very basic level, we are going to there are many types of HVAC systems. We are going to mostly focus on what are called forced air HVAC systems, where the term forced air comes from the fact that we are literally pushing in cool air into the rooms if we are talking about summertime operation and cooling. And so this picture can help, where there is equipment called an air handling unit. So right here, this air handling unit essentially takes air from outside and also some recirculated air from the building itself, and through a series of ducts, which are essentially this network of pipes and highways to distribute the air to every single room or zone of the building. And so we are pushing cool air into the zones. In the zones, we have our water bottles, which are emitting heat, so the cool air becomes hot. And so there's another system which is now pulling this hot air outside, away from the zone itself, so that more air can enter and this heat exchange inside the zone can take place. Right, so this is the basic principle of a forced air HVAC system. So this air which is getting sent out, let me quickly change my control. So this is not literally smoke. It's just to distinguish that this is relief air or return air. It's essentially hotter air than the supply air. It goes back through its own separate duct system. It's almost like this is the blood circulation system for a building. And I say that for a reason, because in the next module, you will learn about blood circulation systems a lot. But this is different from like a chimney or a furnace, which is directly just taking air and sending it out to the, essentially, it's eliminating smoke or other polluted air. So this is the basic functioning, and the key component which makes everything work is this thing called the AHU, or air handling unit, or air handling system. Right? So what does this do? It does these 3 things. It's actually pretty complex, and we'll break it down into what the individual components of the system are. But AHU, it delivers essentially air to the zones, air at a specific desired temperature. Or the correct name for this air is conditioned air. Air outside the building is regular ambient air. Inside the building, we have conditioned air, where it has been conditioned or treated to be at some good temperature, humidity, and less sort of particulate matter, and so on and so forth. So here is like a flow diagram of how this air handling system works. I'll show you some animations in a bit, but let's say this is the air handling box. We take in some fresh air from the outside world, and we actually mix it from some recirculated air. So, and the percentage of this mix of fresh air and recirculated air is decided by some valves or dampers. Right? If they are fully open, then you are just taking in everything. So this air comes in. Within the AHU, it gets treated for particulate matter, for temperature, and for humidity. And I'll tell you how that happens. But the output of the AHU is some supply air. So if we are talking about cooling operation, the supply air is at, say, 55 degree Fahrenheit. It's pretty cold. It's actually much, much colder than what most room temperatures are. So we cool the air down at 55 degree Fahrenheit, and then we send it to the rooms through some other equipment as well, which I'll describe in just a second. In the room, this heat exchange occurs where we get some desired air at whatever thermostat setting we are at. I'm trying to locate where the thermostat in this room is. And the output of that heat exchange is that some air is then sent back and just sent outside the building, but a part of that return air can be also recirculated. Why do we recirculate air? Because it has been conditioned, right? So it takes some energy to condition fresh air. So we can recirculate some amount, but not too much, right? There has to be some fresh air brought in because this recirculated air is high in all the COX gases. Right, so if you go into any room after today, you will see all these vents and these ducts. These are meant for this supply and return. Right, so every room will have, I'm guessing, these squares over here, which are kind of evenly distributed. They are supply, and this ventilation system right in the middle of the room is return. That's my guess. I'm not sure. But every room will have a supply and a return duct, ventilation system. So the same story, but in like 3D or more detail. If we break down the air handling unit itself, again, outside air comes in. How do you actually condition the air is the next question. So let's talk just about temperature first. Inside the air handler, there are some heat exchangers or some coils. So let's say we want to cool this air. What is happening without us realizing is inside every air handler, we are continuously circulating chilled water. So this is the first transfer from an air to like a liquid, right? So outside air is coming in. We want to send out 55 degree Fahrenheit air out. So we have to chill or cool that air in the first place. So a heat exchange takes place over here. Then we send that air into the rooms as supply air. Some thermodynamic exchange takes place in the rooms. Out comes return air from the room at much higher temperature than 55 if it actually did something. And then there's another fan which is sending some percentage of that air as exhaust, and there's a sort of mixing valve over here which is recirculating the air as well. Right, so this is the air handling unit. The key components are some series of dampers and fans. So this fan is for pushing the air to every zone that this AHU is serving, and this fan is to sort of extract the air, suck that air, relief air out back, and either send it back or recirculate it with the fresh air. Okay, so that's the first component. This is what the actual equipment looks like in many cases. So now the next time you see the rooftop of a building from a flight or from a skyscraper, all those things that you see, it's probably a AHU. Okay. So I just said right now that the supply fan of the air handler, and once again this picture is maybe too dim, so let's highlight what I'm talking about. So we have this mixing of return and outside air. You have this cooling coil, and you have a fan, and you are sending out conditioned 55 degree Fahrenheit chilled air into the rooms. But 55 is just too cold to be sent to the room, right? So mostly rooms are at good temperature, could be like 72, 74. Most people like that sort of a comfortable range. So what happens is, before the air is in fact sent to the room itself, there can be some local adjustments that you can do to meet the expectation of the thermal load of the room. And usually there are two kinds of adjustments. One is that you can only adjust the temperature of the air locally, right? So you can do that. Let's say you have something called a reheat coil at the entrance of this room. So this room will have something called a constant air volume box, Why is it constant air volume? Because it's not going to mess up with the flow of air. It's only going to adjust the temperature of the air locally. So if the desired air temperature in a room is 72, you will actually reheat from 55 to 72 to meet that goal. Right? So you do that, and when you don't, when your local adjustment is not messing the volume of the air which is being sent to a zone, that sort of a terminal unit is called a constant air volume. So obviously, if this is constant, there's also something called a variable air volume unit, or a VAV, in which you can control locally both the temperature and the flow of chilled air into a zone. Right? So to give you some intuition about this, when you set your thermostat at, say, 72, we look at the 55 Fahrenheit air, and we look at, your desired temperature is 72, but maybe the current temperature in the room is 75. It's too hot. You need to cool the room. So what you can do is, first of all, the 55 Fahrenheit air which is coming, you can stop reheating this. Right? If the temperature is too high, you don't need to reheat. You can actually let the cool air go into the zone as is. If even that is not enough, the local unit can increase its dampers or valves so that the flow of air is also increased. Right? So two things can govern how fast we can cool or heat a space. One is the absolute temperature of the supply air, and the other is the mass flow rate of that supply air as well. So what I'm trying to tell you is that a VAV, or a variable air volume terminal unit, can do both. And most buildings, modern buildings, of course, have VAV units and not CAV units. The reason, again, I introduce these terms is only because they are very relevant to sort of the model that we will make later. So is the air side system or the air loop clear on what the air handling system does? Any questions on this? All right, so another definition, we'll revisit this. I'm just introducing that because it's very relevant to one of the models. So just about 2 minutes ago, I said that the return also has its own sequence of pipes and ducts. Sometimes, especially in older buildings or in very simple home constructions, what you will find is, rather than having a dedicated network of return air ducts, as is shown on the left-hand side, there's no dedicated network, but instead there's an entire space itself from which this air can be returned. Right? So we are just sort of taking the air back into this yellow zone, and this entire zone behaves like the return air system in this case. So there's a name for this configuration. This is called a return air plenum, and I just want to introduce this term because the building that we will model, instead of having an air duct system, it will have a plenum over there. The functioning is still the same, right? It's responsible for taking out this hot air back or return air back into outside the building. So this is the air side, right? I just said that. So to think about it again, we are getting cool air into the zone. The cool air is taking the heat out of the zone. This heat is being generated by us as the hot water bottles, and so this return air now is at a higher temperature. Some of this return air is going to get circulated back along with the outside air as well. So essentially what has happened is, the heat in the air of this room or this zone has been transferred into this air handling unit loop. But this air handling unit doesn't want this hot potato either. It's going to discharge that heat that it has into a water system, especially where we have this cooling coil. Right? So the interface in the air handling unit is this air-water interface. So once again, you get this return air back from the rooms. This return air is going to be at a higher temperature than 55 Fahrenheit because that's what it has done. It has taken the heat out in the zone. But we want to cool it back to 55. In this hypothetical example, let's assume we are just recirculating. We are not taking in fresh air from the outside, even though that doesn't happen in reality. So we have to bring this hot air back to 55. So it has to discharge, get rid of that heat to some other medium. And that's happening with these heating coils and these cooling coils. So in the case of cooling, we are circulating chilled water into this copper tubing or copper coils, and the fan is blowing the air past these copper coils, and the rate of circulation of the water and the temperature of the water and how fast you blow past these copper tubes regulates how cool the air will become. But essentially what is happening is the heat from the rooms now, which was being carried by the return and supply air loop, is now getting pushed to the chilled water loop. So we send chilled water into the coil, let's say at 42 degree Fahrenheit, and it extracts the heat from the return air, reducing its temperature to 55, but in doing so, the temperature of the water itself will increase to some other number which is higher than 42. Make sense? It's simple heat transfer. This is how radiators of your cars also work. They have this, heat exchanger inside. Okay, so question becomes, now we have taken this heat which we wanted to get rid of, somehow managed to transfer that into water, but then who's maintaining this water temperature? So there's an equipment called a chiller, which has this loop now, right? So a chiller, it sends out chilled water, which is this arrow at 42 degree Fahrenheit, into an air handling unit. Out comes water which is no longer chilled, and when it enters the chiller, that water again has to be brought back to the 42 degree Fahrenheit because it has a water loop. So inside the chiller, there is actually a refrigerant which is very, very efficient in doing this heat transfer. Right, so usually like water will go out at 42 degree Fahrenheit and come back at maybe 60 or 70 Fahrenheit, which is extremely hot. So you have to have this delta of like 20 degree Fahrenheit done very, very efficiently. So chillers are specialized equipments where I am not showing this here, but inside the chiller there is a refrigerant, just like inside every refrigerator you can buy in the market today or an air conditioning unit. And that refrigerant has the property that it can exchange this heat from a water loop very, very efficiently. But then the question will again propagate. The refrigerant was going to exchange heat, but the temperature of the refrigerant is going to increase now. So you are still passing the hot potato. So the final loop is what is called this cooling tower loop or a condenser loop. And what happens here is this other interface of the chiller. So you can think of a chiller as a intermediate between the buildings and the outside environment. It's circulating chilled water, so in some sense, it's actually absorbing the heat from every room in every building on grounds. Right? So this air handler unit could be across many, many buildings, not a single building. And then to reject its own refrigerant heat, it has another water loop where water gets the heat from the refrigerant, and then the eventual discard of the heat to the environment takes place in something called a cooling tower. In a cooling tower, you have water at a high temperature. A fan is blowing the water down into like a pool, and in doing so, it's breaking the water into very, very minute droplets, almost like a mist. And when this mist falls a certain height, it eventually rejects the heat to the outside air. Okay, so we've come all the way from every room now talking about this massive equipment called a cooling tower, which is utilizing property of mist of water falling in a certain height at a certain speed regulated by a fan to reject that heat to the outside world. And so it cools that water down, that water goes back into the chiller, picks up the refrigerant heat flow and rejects it to the environment again. So questions on this entire massive system. I'll show you some more pictures later. In fact, I have access to the university's sort of online portal to control these systems, and I'll show you how chilled water is being sent to this classroom in just a second. Okay, so just to like refresh your memory again, right? So we've already studied, or not studied. I already mentioned this in the first lecture that for a large campus with 180 buildings, the chilled water plant consumes a lot of electricity. So here's a view of a campus or a university where everything which is blue is a building, not a zone, it's a building with hundreds of zones, and everything which is pink is like a chiller. So this is the chilled water distribution network of a university, or example of that. So you have many, many chillers across the campus, and they're serving different buildings. So in some sense, it's very similar to how a single building operates. So an air handler unit is serving multiple rooms. The chiller is sort of doing the same, but instead of rooms, it's serving multiple buildings itself. So here's what cooling towers look like. They are massive mechanical equipment, and what I was saying earlier is this hot water or water at a higher temperature comes from the chiller. Why is this at a higher temperature? Because this has taken the heat from the refrigerant inside the chiller, which actually took the heat from the water which was coming back from the buildings. So this water at higher temperature goes into this cooling tower. It's, this pump will actually send it to a certain height. These fans regulate how fast this mist is going to drop, but here is where the exchange with the outside environment is taking place. So on certain days which are very humid, this process becomes very difficult to do, because the outside air already has so much humidity that it's not able to exchange heat efficiently. So many, many loops may be needed to get this water down to a certain desired temperature. But on a dry, hot day, this works quite well. Okay, these are what chillers look like from the top. So this is a good summary of these different loops. At the zone level, we had the air handling unit, which circulates cool air into the zones. So this arrow denotes the return air coming from the zones. It has to be cooled down back at 42 degrees Fahrenheit. So that exchange takes place with the heat exchanger. How does this heat exchanger work? We are continuously supplying chilled water into the exchanger. It picks up the heat, and hot water comes out of the heat exchanger. It goes inside the chiller, where there is a heat transfer to a refrigerant, but then the refrigerant becomes hot. It rejects its heat to another loop, which goes to the cooling tower and eventually, is rejected to the environment. So this remarkable, massive matrix always is functioning without us ever noticing, unless something goes down. Okay? So if you take away anything, you should know how this system works from this point onwards in your life. So here's an example of what an actual chiller plant looks like. So this is the one from University of Pennsylvania, where I went to grad school. This is what a chiller looks like. So this is the part which has the refrigerant inside, and you can see, I don't remember the color code, but based on the arrows, you can clearly see, maybe this water is coming from the buildings, this water is going back to the buildings at 42 degrees Fahrenheit, and then the blue curve is the one which goes to the cooling towers. Right? So these are massive equipments, and they consume a lot of electricity as well. So on a hot day, this is what is consuming so much peak power for a campus. Right? So being a cyber physicist, you have to be familiar with this domain. So you spend time next to these chillers and these cooling towers. Okay? Here's me with my biggest fans, which are these massive cooling tower fans. So this is an ugly picture, but it's still effective because it shows everything in the same image. Right? So we have, let's start from the building again. We have outside air coming in. There is a heat exchanger. So chilled water, which is this blue line, goes into the heat exchanger. We have to cool this air at 55 degrees Fahrenheit. So there's a heat exchange over here. We send this 55 degrees Fahrenheit air to the rooms. There's some heat transfer which is not shown on the slide, but the air which comes back is because of this thermal exchange inside the room. And that's why we have to continuously condition this. So as a result of that, this chilled water which has been circulated is also gaining some temperature. Now we have to, this high temperature water, return water, goes into the chiller, and it has to be brought back to its original 42 degrees Fahrenheit set point. So to do so, there is a refrigerant loop, which is this tiny little pink and green loop over here. So refrigerant is a special fluid slash liquid, it's a mix of fluid and gas sometimes, which is very efficient at doing this exchange between the building facing water loop of the chiller. But then to cool the refrigerant down, we have another water loop, which is the environment facing side of the chiller, where we'll take some chilled water and pump it into a cooling tower, make it into a mist, drop it through a certain height at a certain flow, and it results in some cool water which can be used again to sort of replenish this refrigerant. So you see all 4 loops in this picture. I originally said there are 5 loops. The 5th loop is what you call the control loop. It's not a physical phenomena, it's a logical cyber loop, not a physical loop. So this picture should really clarify how the system works. So if you have any doubts or questions, you should always sort of refer to this one. Okay, so I don't know about you, but I just find this entire thing quite fascinating, how it works. So let's talk about something which occurs at the zone level now, right? We haven't really described that. So this is the first equation of the day. And don't worry, you have to not remember this. We will understand this during next week when we try to model stuff. But essentially, what is happening in the zone is you have supply air coming in at, say, temperature T supply air, and you have return air going out at, say, temperature T return air. So all this equation is telling you is that if you look at the heat flow or the thermal heat exchange within a zone, if you just measure the supply and the return air and you know the rate of flow of air itself, don't worry if you haven't seen this equation in many, many years. The heat flow is the mass flow rate times some specific heat of the air times delta T. You can calculate what's the actual heat load or demand of the zone just by looking at the mass flow rate of the air, assuming it is constant, and looking at the supply and return temperatures and their differences. That's how much heat you have extracted away from the zone. And so we can describe it mathematically, and we'll use this property to actually build our state space model. So finally, let me talk about the 5th loop, which is the control loop. So you have this amazing system which works 24/7, 365 days. And now let me tell you how actually, so one question is that you have this 55 degree Fahrenheit air or 42 degree Fahrenheit chilled water. So how is this temperature always getting maintained, right? Is someone manually shutting and opening these valves to do this business as usual operation? The answer is, of course, no. This is an automated system. And so the degree of automation is because of many, many small control loops throughout this system. Okay, so let me tell you about some of these control loops. So at a zone level, I told you there's a terminal unit which has 2 options. It has the option of opening the valve into the zone so it can adjust airflow, or it can also locally reheat the air at 55 to adjust the temperature of the air being sent into the zone. So how does it figure out what to do and how much to open this valve, how much to reheat? It all happens based on the thermostat setting, right? So you have a zone where you will have a desired temperature setting, and then this thermostat not only measures the desired reference, it also measures the actual temperature at that point, wherever it's installed. And it's going to look at the mismatch and see whether the room is too cold or too warm compared to your preference. And based on that, it's going to locally adjust these reheat actions or the valves to make sure that the room temperature is close to the desired set point. And so it does that using very, very basic closed loop control. I'm going to say something which some of you may have heard of before. It does this using a PID controller. Okay, so you have a proportional integral derivative controller where it's looking at the error between your desired temperature and room temperature, and it does the valve position or reheat proportional to the error or the derivative of the error or integral of the error. So this is not a control class, so I won't go into details of PID. The same thing actually happens with the air handler unit. Okay, so the air handler unit has to send air at 55. It can do so with 2 mechanisms, by adjusting the rate at which it is pushing the air across the cooling coils, and also adjusting how much the flow of the chilled water occurs in this heat exchanger. So again, there is another PID over here, which is looking at maybe the air is at 57 degree Fahrenheit, but the desired supply air should be at 55. So it will open a valve so that more chilled water can flow through the heat exchanger, or it will start blowing the air faster across the heat exchanger. Again, a local PID. So there are many, many such PIDs. At the chiller, we want to send water out at, say, 42 degree Fahrenheit. There's going to be a set of valves and pumps that will do a local PID to maintain that set point. Okay. In addition, the question now becomes, well, these are local self-regulating PID loops, but now one can ask, why this value of 55? Why do we want the temperature at 72? That's like a user preference, or someone external to this operation is telling the system that send it at 55, send it at 42, let the room be at 74. So those set points, or the references themselves, you can think of them as supervisory control, which are different from local control loops, which are PID. The reason why they are supervisory is that when you want to do things like demand response, you will change these references. You will not change the working of the loops. So you will say, well, instead of having the room at 72 degree Fahrenheit between 2 to 4 p.m. when there's going to be a peak and I have to curtail, let me change the reference to 75 just for 2 hours. Let me change the reference from 55 to 57. Let me start sending water at 44 rather than 42. And these minute changes, if we can predict what effect they will have on the electricity consumption, on the thermal comfort, then we have essentially succeeded in modeling the system for predictive control. So all of the story was to get to this point. So just to be crystal clear, what I was talking about as a local loop, the thermostat in the room is going to compare the reference set point, which some human or user has specified, or some high-level AI controller has specified. It's going to look at the mismatch between the set point and the actual room temperature coming from the thermocouple in the room. Based on the mismatch, it uses PID to either open dampers or send a reheat signal to this VAV box, and out comes the air at a temperature which we think will get us closer to this mismatch. So this is happening at the room level. The same thing is happening at the AHU, air handling level, where you have a supply air temperature, which is SAT, at 55. But we look at the current supply air temperature that may be higher or lower. And so we can increase the flow or increase this chilled water through the heat exchanger as well. So before I get to this, any questions so far about all of HVAC? This is all we need to know about HVAC. There's many, many layers more, and also to be clear, we will not model all these mechanical systems. We'll only be modeling the thermal dynamics of zones. So we won't be studying how do you model an air handler. That's an advanced topic. But any questions on the operations, the loop, everything makes sense? Okay, good. So in reality, I just want to say this because I always want to keep one foot in the real world and one on the slides. In reality, most PIDs, they may not be that well tuned. So if that sentence didn't make sense, don't worry. In the real world, many systems, they work in this manner, where the user specifies some desired temperature, which is not actually shown in this picture, but we create a band or a region around that desired temperature, and we let the system just ride the upper and lower limits of this region. So in some sense, you will let the temperature increase from the desired until it reaches some upper limit, after which you will start sort of controlling the reheat and the valve so that the temperature starts dropping. You will overshoot your desired temperature, hit some lower value, and then go up and down again. So the sort of bang-bang control is very commonly done, and this is an example of a rule-based controller. Okay, this is how buildings are set as rules. The facilities managers aren't really tweaking with the gains of PID controllers. They are just specifying, I want this band to be narrow or very large, or the narrower it is, the more high fidelity temperature control you want for your zone. The larger this band is, the more flexibility you have in terms of how much deviation you can have from the reference. Okay? It's just sort of a moot point over there that we'll revisit. So don't get too excited because it says next lecture, because I will show you some other stuff too. In the next lecture, we will look at how do you model the temperature dynamics of the zone using something called a RC network, where the resistances and the capacitances of this network, they are not electrical, they are thermal. Right? That's really, now we are getting into the weeds of this module 1. And so we look at the differential equations that describe this dynamics and put together a state space model to describe the temperature dynamics of the zone. And we are doing this painful exercise for just one purpose, so that you get into the habit of knowing how do you model a dynamical system with physics-based first principles. So let me actually quickly show you that all of this that you looked at today also exists in the real world. Okay, so this is an overview of the entire heating, ventilation, air conditioning system for the entire university. Okay, so I hope this is visible. Okay, it is. So let me first show you the chilled water loops. So this is the entire map of the grounds, and we have many, many chillers. So these are all names of different chillers, and if you look closely, this is where Scott Stadium is, right next to us. And so this region is what is serving this building right now. So let me just click on this real quick. So this is a high resolution view of that again. Here is the stadium, and you see all this network of pipes which is serving every building, right? So let's try to find, this is Rice Hall, this is Olson Hall, this is where we are at right now. And there are two chillers which are serving this part of the grounds. One is in the gym, the Aquatic and Fitness Center. The other one is near the chemistry building, actually on top of the chemistry building, if you have ever been there or seen it. So let's go one step deeper. It's like Inception. It'll take a second to load. So this is the real-time view of what is happening in that chiller in the chemistry building. Okay, so first of all, we have 3 chillers, but only 2 of them are operational right now, because it's maybe not hot today. I think it's pretty good compared to a few weeks ago. But let's see, so the output of this chiller is water at 43.9 and 40, so roughly 42 Fahrenheit. That's what the output. This is being sent to the building. So let's track these pipes down. So this pipe at 42 merges with chiller 1. Nothing is happening in chiller 3. So this 42 degree Fahrenheit water is getting sent where? Let's keep going. It's getting sent to distribution. The distribution is the buildings that this chiller is serving. It's not serving just Olson Hall, it's serving probably maybe 10 or 12 buildings. This single chiller with this chiller plant with 2 active chillers. Okay, so it goes to distribution. At every building, there's some air handler. We'll see the air handler for this room in just a second. And then return water comes back at 55. So we are sending at 42, it's coming back at 55. So we have to reject this heat from all these buildings. So on the other side of the chiller, this light blue or cyan pipe network is the condenser part, right? So we take this chilled water at, let's say 81 Fahrenheit. We send it to these cooling towers. All 3 are working. Actually, all 3 are working at 100% right now. So we are sending it to the cooling towers. The mist is getting created. And from 82 degree Fahrenheit, we are receiving 73 degree Fahrenheit water back. So we have rejected that thermal mass to the environment. And this 73 water is getting sent back through these pumps into the chiller again, where it's going to get back to 82 because it's rejecting this heat from 55 to 42. Good so far? So this is the chilled water side, and like we said that it's serving, I'm sure there's a view of this where it will give me a list of the buildings, but just on visual inspection, it's serving all of this engineering complex. And then this part serves most of these other buildings on the north side of the campus. So that's the chilled water side. Let's also quickly look at the air system. So here is Olson Hall. Let's go to Olson Hall. So this is Olson Hall from a HVAC viewpoint. We are in the basement right now. So we are in the basement. In the basement, we are in 018. So this is the terminal unit of 018. And what you can see is that okay, I think something is wrong here because we shouldn't be receiving air at 87. So maybe it's some sensor is off or something. But what you can see is, if it loads enough, well, we can at least see that we are getting served by this air handler unit B. So let's actually go to air handler unit B. Yeah, so this is the picture I really want you to see. So this is the air handler unit responsible for sending air to this zone. It's also sending air to other zones, but in particular to this zone. Right, so outside air comes in. There's a series of valves here that I didn't go into details because they are not relevant to our discussion. But this air is coming in. It's almost like at 74, 72, which is the temperature outside, I believe. And then it goes through this chilled water loop. Where is this chilled water coming from? From that chemistry chiller that we just saw. It's sending water at 42. We can regulate how much flow we want at this heat exchanger. It's 86% valve position also tells you this local PID state. Then there's a fan, which is also getting, it can operate between 0 to 100 sort of RPM range. So we have conditioned this air to be at 55 or roughly 55, 53 to be exact. It's getting sent to 018 and other zones too. And then air comes back again at around 75 from these zones. None of it is getting sent off. This is closed. The return valve is closed right now. So we want to use all of the return air right now. So maybe we are not operating in this ventilation mode. But then this comes back. So all of this air comes back and goes through this mechanism again. And here is where the heat transfer with the chilled water is taking place. Okay. So any questions on what are HVAC systems? So there's many other aspects that are very interesting as well, but I don't want to take too much of time today. But to just tell you, this is the equivalent of that block diagram that I showed you on the slide. It's literally, this is the rule-based logic of figuring out what that band is. I know it's not visible, so it doesn't make sense to point out at arbitrary things and tell you what they are. But that logic, that rule-based mechanism of how the building runs, here's a visualization of that. Okay, so starting next week onwards, we will jump into how do we model this. There's a question, yeah. You can't get access to this, yeah. For security reasons and also because, well, you can come do research with me and then you'll have access to this. All right, so that was the domain part of energy systems. Now we'll get into the modeling and the principles part, okay? I'll see you next week.